Hi, this is Saturday Extra and it's Physical Sciences, Grade 12. My name is Tinyiko Kosa and I welcome you into this lesson. I hope we will be together until the end. Now, today we're going to talk about electromagnetic radiation and color. Now, specifically in this section, we're going to talk about the spectrum, the electromagnetic spectrum. EM there stands for electromagnetic. We will also look at the characteristics of EM waves, electromagnetic waves. And then we will begin to talk about color, how we perceive things, how we see things. Now, under color, we will be talking, one, about the addition of light. Again, under color, we will also be talking about subtraction of light. Now let's have a look at the electromagnetic spectrum. Now the electromagnetic spectrum consists basically of three sections. I look at them as having three sections because we've got this first part here, and we have got this middle part here, and we also have that last part there. Now this part here, let me call it A, and that one B. And then I'll leave the middle part as the middle part. Let's call it M, if you like. Now, this A part here is a section where we have got electromagnetic waves that have got very low frequency. So this side, low frequency, low frequency. And when we move towards B, this side here, we see that we begin to have high frequency. So this is a region of low frequency, and whilst this B region, as I've called it, is a region of high frequency. So electromagnetic radiation ranges from low frequency waves to high frequency waves. And when we have low frequency, we know that that is linked to long wavelengths. So you will see here, if we say here we've got low frequency, you could see that this part here up to that point, this part here, the waves are sort of, the wave crests and troughs are sort of far apart from each other, such that it shows that we've got longer wavelengths this side. So long wavelength, that symbol there for wavelength. And from this point here, this going that way, you can see that this crests and troughs are actually bunching onto each other, and they're so close to each other, and that gives you, or that's an indication for high frequency. And when there is a high frequency, that again is related to the wavelength, and the way they are related is such that if you've got high frequency, you're going to have short wavelengths. So the relationship between wavelength and frequency is such that when the other is increasing, the other one is decreasing. We've got an inverse relationship between wavelength and frequencies. Now, let's move on and look at the characteristics of electromagnetic waves. But perhaps before moving on to that point, there is one section that perhaps we need to look at quickly before we go there, because it's going to help us to understand something we're going to. The middle section. The middle section there, you would see it's written the visible spectra. Now, what does that mean? What that means is that what we have on the left here is not visible. So it's invisible. And what we have on the right side here is also invisible. We can't see it with our naked eye. But then something in the middle here, which is the visible section of the electromagnetic spectrum, is what we can see. And let's look at what is happening here. Here in this visible spectrum, we've got colors that we can see, that we can perceive with our naked eyes. These colors here, if you check, you start there with some red color, and you end somewhere there with some indigo color, violet color. So you've got a range of colors from red here to violet at the end there. Now, if you look at this, I want us to link this right from the beginning, because the spectrum, the EM spectrum here, is also showing that to us immediately, that even with our visible spectrum, there are those colors that are associated with low frequencies and high frequencies. So you would see that red is right at the far end of our spectrum, and it is on the left-hand side. And the left-hand side says what? It says low frequency. And by saying low frequency, we are saying long wavelengths. So this means that the red light, or a red color, would have the lowest frequency and the longest wavelength. But then on the other end, with violet, V there, it is associated, of course, with high frequency. And because it is associated with high frequency, it is therefore a color that has, or light color that has, short wavelengths. Let's look at this white light. Actually, the visible spectrum here, it consists of the white light. This is where we are able to see. Anything on the left we can't see, anything on the right we can't see. Now, the white color, or the white light, is actually something that is formed of several colors. It has got the red end here, as you can see, the red part. It has also some color right at the end there. It's one light that is actually harmful to human beings or life on Earth, and we call this violet light. So it ranges from red to violet. Now, when we look at this, we said earlier on that anything towards the left, on the left side, is actually something of low frequency. That tells us that red sitting down here has got low frequency. At the same time, if we look at violet right at the end on the right, it is associated with high frequency, and high frequency, we know that that is associated with short wavelength. Now, if we are to unpack these colors that form the white light, let's now have some space down here to write our colors. You would see here we're starting with red. So there is red in white color, or white light. And next to red, we begin to see some orange there forming. So we would have O for orange. And next to orange, of course, very close to each other there, we have yellow. So I'll have Y for yellow. And just after yellow, we begin to have some green there forming. So there is green in white light. After that, we have some blue forming. So that will be blue light, or blue color of light. And after blue, there is some deep blue color, but not necessarily exactly blue. And we call that color, we're not so used to talking about it, we call it indigo. So it's I, we'll have capital letter I for indigo. And right at the end, of course, is what I explained earlier on. It's violent. So I would have V for it there. So the spectrum of white color, of white light, is formed by red, orange, yellow, green, blue, indigo, and violet. So we've got about 7 colors here. So these are 7 colors forming the white color. So this is sometimes referred to as the spectrum of white light. The spectrum of white light. Spectrum of white light. Okay, so that's what we have here now. So let's move on and look at the characteristics of those electromagnetic waves. How are they? How do they behave? Now, all electromagnetic waves are said to you when you see capital letter E and M together, it stands for electromagnetic waves. All electromagnetic waves are caused by the acceleration of charged particles. Now, this is very important. Charged particles, remember, you can, with charge, we can have a plus charge, we can have a minus charge. So these particles need to be charged to be able to create or to cause electromagnetic radiation or waves. Now, these waves are transverse waves. Okay? Now, transverse waves, I need to come back to this one. Transverse waves, what types of waves are those? These are waves that move up and down, or the particles are actually vibrating in an up and down motion, okay? Whilst the wave is moving at a right angle to that particular motion. Opposed to what we call longitudinal waves. You'll remember longitudinal waves with sound, that longitudinal waves will consist of rate refractions and compressions. So these waves move in the same direction as the wave. But then transverse waves move or have particles vibrating at right angles to the direction of the wave. If that is the direction of the wave, the particles are moving in that direction, or the wave motion is in that direction. So you have got particles moving at the right angle to the direction of the wave. So such waves are the waves that we draw in that fashion. So these are transverse waves. They consist, of course, like I've shown in the previous slide, of crests and troughs. So you've got the top part of the wave here. You know it very well. We call that the crest. You would have the bottom part of the wave called the trough. Now, these electromagnetic waves are in that particular format. They don't occur in the form of longitudinal waves, but they occur in the form of transverse waves. Now, these transverse waves are made up of changing magnetic and electric fields vibrating at right angles to each other. Now, we have got two types of fields here. We have got magnetic field and we have got an electric field. These two together, they vibrate at right angle to each other. Right angle, remember, 90-degree angle between the arms. So that is what we mean by right angle. But then these quantities here are waves, and they are said to be vibrating at 90 degrees to each other. Let's have a look at this diagram here to illustrate how the electric field and the magnetic field, as caused by a moving or accelerating charged particle, vibrate in relation to each other. If we take the blue part, this part, to be representing the magnetic wave, then let's use the red to represent the electric field wave. So this wave here is due to the magnetic field, and that wave there is due to the electric field. Now, if I draw a line here that could be continuous in that way, you would see that this blue one is sort of protruding out of the screen as you look at it, and this one is vertically moving, or the red one is vertically moving upward, whilst this one is protruding towards us here, or towards me from the screen. Now that means that they are at right angle to each other. So the red one is there. Allow me to do that. And let me try and see if I can get another nice color that can work with this one. So say that represents the magnetic field wave. So this blue one is at right angle to the red one, that one. Okay, so that we need to know, that these two electromagnetic waves vibrate or move against each other at right angle. So when you have your magnetic field wave moving in that way or towards you, the other one should be moving upwards. So if that is the upwards, maybe it's something coming towards you, I can't be able to draw it, but it's something like that. They are moving their direction as such that they form a right angle between them. Right. Now, what else can we say about these electromagnetic waves? There are two more things that are very important that I need to mention about electromagnetic waves. Here is one. These electromagnetic waves travel in a vacuum. Now, what is a vacuum? This, it's space without air. A vacuum, it's space without air. So electromagnetic radiation, or waves, would move in a vacuum at a constant speed of 3 by 10 to the power 8 meters per second. Now that's a very fast speed, and it also accounts for why light is able to reach us on Earth from the sun when the sun is so far from us, but reaching us quite quickly. It's because the sun emits electromagnetic radiation. The light that we see is electromagnetic radiation from the sun, and it travels through the vacuum. And of course, as it reaches the Earth, it then enters into into the atmosphere where the gases begin to be present. But the fact that it is able to move in that vacuum and penetrate into the Earth and in such fast speed is because of this ability of electromagnetic waves being able to move in a vacuum at speed of 3 by 10 to the power 8 meters per second. Now, you would know that we're talking about electromagnetic waves, magnetic radiation, as having the wave nature. Or in other words, these are actually waves. Now, if they are waves, definitely they should comply with the wave equation. Now, the wave equation is that the velocity of a wave is always given by the frequency of the waves times the wavelength of the wave. That's the wave equation. But then because here we're talking about specific waves, we're talking about electromagnetic radiation and we know the constant speed at which they travel. This constant speed at which they travel is given a symbol c. So we say c to mean the speed of electromagnetic radiation waves. And as we call it c, and that is its value, that is why here instead of v we say for electromagnetic waves we are going to use c there. That c is actually v, but it is a constant and therefore we use a specific letter to denote it, c, meaning the velocity of the electromagnetic radiation. Okay, now this electromagnetic radiation, we also need to know that they carry specific amount of energy. Now remember, when we go back to waves in grade 10, we know that waves carry energy. Okay? Waves carry energy. Now, waves carry energy. So if electromagnetic radiation is actually waves, therefore electromagnetic radiation should be carrying energy. So what is sort of special about this kind of waves is that they don't just carry energy that we find by trying to experiment with that particular wave or try to determine the energy that they are getting there or they are carrying. But with electromagnetic waves or electromagnetic radiation, they carry specific amount of energy. In other words, if that wave is a gamma wave, it will carry energy related to gamma and nothing less or nothing more. So these electromagnetic waves carry specific amount of energy which is directly proportional to their frequency according to Planck's equation. And Planck's equation is what we have there. Energy equals Planck's constant h times the frequency of the wave. Now, I'm not going to talk much about these for now. There's a whole session on on photoelectric effect where we're going to talk more about this. But I want you to be aware that these EM waves carry specific. By specific, we are saying they carry that particular amount of energy. It cannot be more, it cannot be less. And that energy is defined by that equation there. And this equation here, like I said, we'll talk more about it in one of the oncoming lessons. Right. Let's now move on to do some examples. I've got example 1 here. What is the wavelength of orange light, which has a frequency of 5.0 by 10 to the power 14 hertz? Now, for us to calculate for this, you would see here what is given to us is 1, we are told that the frequency of the light we're talking about, the orange light, is 5.0 by 10 to the power 14 hertz. Right? That's what is given to us. What we need to find out is we need to find out what the wavelength is. So for lambda, we're going to have a question mark. Now, if you're looking at the information given to us, you would say, but how are we then going to calculate for these unknown, the wavelength, when we are only given one particular value, which is that of the frequency? What is given to us is the frequency here. I hope you can quickly answer yourself in that question. The reason is that we don't have to give you the speed of of light here because it's a constant and it's given to you. So you need to know that although it is not cited in the equation or in the information here, we need to know that C, it's constant. This is the velocity of electromagnetic radiation. It's given as 3 by 10 to the power 8 meters per second. Okay? So that is also given to us. And therefore, for us to find lambda or the wavelength, we can then make use of the wave equation. Now, this is, again, a special wave equation. Why special wave equation? Because we have C here that is constant. It's special in that way. This C here, as we know, is the 3 by 10 to the power 8 meters per second. Now let's start to substitute into the formula so that we can be able to calculate for lambda. Like I always say, remember, we also practicing for the exam. You are not going to try and fiddle with this formula to try and find out what lambda is. Although that is not actually forbidden, you would know that lambda is equal to C over frequency from this equation here. But you don't have to come here. You don't have to come here because you lose marks by making mistakes when you change the subject of the formula. So for the sake of you making sure that you get maximum marks in substituting your given values in your formula, rather leave the formula as is and substitute what is given to you. Now let's go and do exactly that into this formula. C is 3 by 10 to the power 8. So in place of C, I write that down. Equals F is given to me. It's 5 by 10 to the power 14. So it's 5 by 10 to the power 14 times. The wavelength is what I am looking for, so I would leave it as is. Now, from what I have here, I can therefore say that lambda is given by 3 by 10 to the power 8 divided by 5 by 10 to the power 14, right? And from there, I can get the answer. Now, for us to work that out, we need a calculator. Take out your calculator and work this out with me. Now, we have 3 by 10 to the power 8 divided by 5 by 10 to the power 14. And what is the answer? The answer is 3 to the power 5 with so many zeros there. But then how do we quickly get the answer in the way we want it? You press your sign there, the SD sign there, and you get your answer. Do not forget that because it might catch up with you in the exam. So you would see that your answer is 6 by 10 to the power minus 7 meters. That is your answer. But you would have seen that the answer, as you have it in the calculator there, is you have got so many, you can write it in that way. But what I have done is actually to write it in, it's actually to write it in what we call scientific notation. I think you know that because that is very basic for you to use when you have got numbers like that. You don't have to see all those zeros, string of zeros. You need to write your numbers in scientific notation. Now let's move on. I want us now to look deeply to the white light. Remember what I said earlier about the white light, that it can disperse into several colors ranging from red to violet. And there was a quick way of remembering all those colors forming the white light, and I was taught by one of my teachers years back. I was still doing standard 5, which is currently called grade 7. Now, what he did was to show me, or way of remembering this, he would say, always say that you have got Roy G. Bev. All right? And you will remember that R is for red, O for orange, yellow, Y for yellow, and G for green, B for blue, I for indigo, and V for violet. So that was a quick way for me to remember this, and I never forgot it since doing standard 5. That is years back. Now, let's look at this white light here. Here is white light. It enters a prism. When it enters a prism, it begins to disperse from that point. So we see it splitting into several colors. And we know that those colors are the 7 colors, are the red, orange, yellow, green, blue, indigo, violet. Now, let's check carefully what is happening here. If you look at it from the left, this white light is coming out of A. Then it comes into a glass prism. Okay, it gets into a glass prism. Then when it leaves here, it leaves the glass prism back into air. But something has happened. When it enters the glass prism, we see it dispersing. We also, if we were to use scientific terms, we see here that the light sort of bends, if you like, in that kind of fashion. This bending of light, or this change in direction of light as it moves from one media to another, is called refraction. Now, it is moving from air. Air is said to be less dense. So air is not that dense. But it enters a prism that is more dense. Now, perhaps you want me to explain more on what we mean by a substance being less dense and another being more dense. Less dense simply means that particles are far apart from each other. You would see for SA particles are in that way. So they are far apart from each other, easy to compress, okay, or push aside as well. But here, inside the prism, the particles are so close to each other and they are compact. It's not easy to push them around. So that's what we mean by something being more dense. Particles are close to each other. Now this light here gets into the prism and changes direction. In other words, gets refracted. Changes direction, but when we look at these 7 colors here, which color has bent or has been bent more than the others? You would see here in this far end that this part here, or these colors here, have been bent more than the colors there. Now, this has to do with the frequency. The higher the frequency of light, the bigger the refraction or the change in direction. Now, there's also another thing here that I need to explain about light. Light, having moved from a less dense object into another object, which is, in this case, the glass prism. Allow me to use the terms media. We have got the substance in which the light is moving here, and we will call that the medium. The medium in which light is traveling before getting into the glass is air. It's this. This medium here would have the light moving at a particular speed. So the speed depends on the medium. But when light gets into a new medium here, and the medium this time here is the prism, it is now moving into a new medium, and therefore it cannot be moving at the same speed as it was moving in air. So here it moves in another speed. Why? Because the speed of a wave depends on the medium. Let me write it down here clearly. Speed of a wave depends on the medium in which it is traveling. In which it is traveling. Okay, now that's why we have got, for example, sound, speed of sound in air. We know it to be given most of the time around that value. But the speed of sound in water, for example, it's not the same as 344. So the speed depends on the medium. Now let's look at this and say, then what happens when speed is changing? These frequencies, the frequency of the waves, frequency is not changing. The frequency of the electromagnetic radiation there is not changing. The side with high frequencies are bent more or are changing direction more than the side where you've got low frequencies. And that frequency remains the same. But then the speed of the wave is changing. If the speed of the wave is changing and the frequency is not changing, because we know that from this equation, this speed of a wave is given by f lambda. If f is not changing, definitely lambda, or the wavelength length, should be changing in order for us to have v changing there. V changes because lambda is changing. I want you to get this very clearly. The frequency is not changing, but the wavelength is the quantity that is changing, which results in the change in the speed of the wave, or the electromagnetic wave. When does this happen? It happens when the electromagnetic waves move from one particular medium into another. It could be moving, the electromagnetic waves could be moving from a less dense object into a more dense object, or vice versa. That change is bound to happen. But it doesn't happen because there's change in frequency. Frequency remains constant. What changes is the wavelength of the wave. Right. Let's now continue to look at these frequencies, because these frequencies are related to the colors that we see. Remember the 7 colors of the white light, the electromagnetic radiation. We have got red, we've got orange, yellow, green, blue, violet. Now here you would see that we are given here the wavelength, if you like, the lambda there. We are also given the frequencies there. For a violet light, that will be the wavelength. And you will see it's given to you in nanometers. Can you remember how to move from nanometers into meters? Because we work in meters, always multiply by 10 to the power minus 9 if it's nanometers. Right, so that's what we have. And that will be the frequency of the violet light. So the frequency is decreasing as you go down the table. Why? Because high frequency is on the side of the violet and low frequencies on the side of red. Like I said earlier on, the relationship between lambda and frequency, or wavelength and frequency, is that as the frequency decreases, what is happening to the wavelength? The wavelength should be increasing. So wavelength should be increasing. Need to get this arrow properly here. So wavelength increases as you go down, all right, from violet to red, and frequency is going to the frequency, as we know, if the wavelength is increasing as you go down, the frequency should be increasing as you go up, because the two are inversely proportional to each other. So let me use the arrows to do that. I think the earlier one was not that correct, or not showing the increase. Though now that's how the relationship between frequency and wavelength works. And remember here, because if we talk of this electromagnetic radiation moving in a vacuum, the velocity remains the same. It is c, which is a constant, and it is 3 by 10 to the power 8. Let's now move on. Let's look at some examples again. Here is example 2. A light source has a wavelength of 520 nanometers. So we don't know what type of light is that, but we just know that this source is emitting light with that wavelength. What is the frequency of this light? We can calculate for that frequency, making use of the wave equation for electromagnetic radiation. Remember what it is? It is C equals F lambda. And again, let's substitute into it correctly. We are looking here for number A. We're looking for the frequency of this light. So from C equals F lambda, we can begin to substitute. What is the value of C? C is 3 by 10 to the power 8. What is F? F is what we're looking for, so we'll leave it as it is. Substitute for the value of lambda. Lambda is given to us as 520 nanometers. Nanometers, do we work in nanometers? The answer is no. We work in meters. Therefore, we need to convert nanometers into meters. What do? Remember what we have to do? We have to multiply by 10 to the power minus 9 for us to convert nanometers into meters. So we're moving from nanometers to meters. To do that, we multiply by 10 to the power minus 9. Therefore, F, the frequency, will be given by 3 by 10 to the power 8 divided by 520 by 10 to the power minus 9. And then we can quickly work the answer to that. And what is the answer? Let's use our calculator quickly. We have 3 to exponent 8 divided by 520 to exponent minus 9. And that is the answer. We know now that the frequency is going to be 5.76 or 5.77 by 10 to the power 14. 5.77 by 10 to the power 14 hertz. Now, there's something that I need to show quickly from the calculator. If you look at the answer we got, it's 5.769230769 by 10 to the power 14. Now, people, you don't have to write that number down. Once you write that number down as is, from 5 as it ranges until 10 by 10, by 10 to the power 14, you're not using your scientific notation. You are also not using your skills on conversions, on rounding off decimals. Now, you see here it's 5.769, but I wrote my answer as 5.77. Why? Because it's 5.76 and the next digit after 6 is 9, and that yields a 1 to 6, it makes it 7. But if this 9 was a 4 or 3 or 2 or 1 or 0, I was going to leave it as 5.76 by 10 to the power 14, right? So that is how it would have worked. Now, the other thing is that the exams require you to write your answers. If you've got decimals into it, write your answer to at least, in fact, not to a maximum. You have to write it into 2 decimal places, or decimal numbers. So that's why I have it as 5.77 by 10 to the power 14 hertz. Don't forget that. It's very important for you to remember. Okay, so that's how it works. So that's the example there. But then to the same example, we have got number B. So let's look at what number B wants us to do. Number B says, what color is this light? Now, what do we need to do to know the color of this light? Because it's not given to us. To do that, we can either make use of the wavelength to see where it is in our table, or make use of the frequency. The wavelength is 520, the frequency is 5.77 by 10 to the power 14. The 520 nanometer for wavelength is here, so that is the range. The 5.77, and I need to explain this, 5.77 by 10 to the 14 hertz is here for frequency. Now, why am I having to the power 14 here? Because I'm writing my answer is in scientific notation as 5.77. But if I wrote it as 577, let me use this bottom part here. If I wrote it as 577, I would have written it as 10 as multiplied by 10 to the power 12 hertz. So remember, when you write in scientific notation, so I've moved this comma from there 2 spaces backwards to come to 5.77. So those 2 spaces backward makes it to be 10 to the power 14. So that's how you find it. So the range where the wavelength and the frequency as we calculated is here. It's this range here. So it means that the color we're looking for is green. So in answering our question here would say that when it says what color is this light, it will mean that this light here we're talking about has a green color. So it's a green light. That's what we're talking about. Nice calculation, and I believe you are enjoying doing this. You can enjoy working out frequencies and wavelengths, knowing that the speed of electromagnetic waves or electromagnetic radiation is constant in a vacuum. It is at 3 by 10 to the power 8. Right, let's proceed talking about these colors. Now we're going to specifically begin to talk about colors, how we perceive things, how we see things, and how light helps us to see things. Now, let's come to this section here. We're talking color, and this time we're talking addition of light. Now, when we add lights of different colors together, or to be specific, of different frequencies together, what other colors do we come up with? Now, in light, we have what we call primary colors. Primary colors: red, green, blue. This is what we call primary colors. So we have red, we have green, we have blue. These are primary colors. They are primary colors because together they give us white light, white color of light. Now, apart from the primary colors, we can have what we call secondary colors. Secondary colors, one, we have what we call magenta. We'll explain more about it. We have yellow, and then we have cyan. These are secondary colors. We get secondary colors by adding primary colors. Adding any two of the primary colors, we get secondary colors. Right. Now let's quickly go back to this color picture here to see how it sort of gives us a nice summary on how we mix colors together of light and get certain colors. Now here you would see you've got green and red. Now when green and red lights are put together, we get yellow light. And that's a secondary color. It's a secondary color because it is found by adding two primary colors. In this case, it's red and green. Here, we can also have red and blue added together. When we have those two added together, we have, or we produce, light color called magenta. And we can also have these other two primary colors, blue and green, added together, and we have a secondary color called cyan. Now, I also want you to have a look at what is happening here. Can you see what is happening there? What color do we have there? We have white color. Now, remember what I said about primary colors. The primary colors, we call them primary colors as they are because you add the three of them, you go to a white color of light. So at that point here, all the three colors meet. The blue, the green, and the red come together, and we have white color of light. And this is called addition of color or of light. We're adding lights together and produce other colors of light. And you would, I think practically you would know that when you are in concerts, you are in functions, music festivals, you will see lights of different colors somewhere along You know, as the light is shown on the stage, sometimes you see different colors. Sometimes someone on stage is having a certain color of shade, but that shade seems to have several colors. That is because of the addition and subtraction. But I will talk about subtraction later on. But the addition of color leads to formation of other colors that we see. Now, I have explained to you the primary colors and the secondary colors. Let's just have a look at some example here. And here we're saying, when you're watching television, 3 beams of light are used to make all the colors that you see. What are the colors of these beams of light? Okay, so the 3 beams of light. We know these are our primary colors, so we have them as red, as green, and as blue. Okay, these are the colors that are used on a television screen for us to see those images. And if you can look carefully on your TV set, you would see there's dots, the red, green, blue dots on the screen. That's what gives us the color, right? And from that, we can get every other color that we would like to have. Now, how do these beams, that's number B, how do these beams make a black image? Black image. Now, a black image would always result when there is no existence, okay? No existence of any of the 3 colors. In other words, if you take away the 3 primary colors, what you will see is black. No existence of any of the 3 primary colors. Okay? Primary colors. They are not existing. So if they are not existing, then you have black. There is nothing. In other words, black is absence of color. Right. Let's move on. Let's look at this last one here. What combination of light beams is used to produce yellow image? Now, perhaps we need to refer back here so that we see that this is not something to crack our skulls about. We want to produce a yellow image. Now, what combination are we going to have of light colors that are going to give us the yellow image? So we would have a combination of red and green. Red and green gives us yellow. So our answer to this part here would be to say, for us to get a yellow image, we will need a combination of red and green. Okay, so that will give us yellow image. Okay, let's move on. Now, we have so far, in terms of color, spoken about the addition of light from 1 or 2 types of colors to another. We have looked at our primary colors of light. We have looked at our secondary colors of light. The primary colors of light, red, green, and blue. Secondary colors of light, it's yellow, magenta, and cyan. That is very important for you to know. Now, let's move on to something called subtraction of color, all right, or subtraction of light. It is, of course, around color. Now, how do you subtract light? In life, we have got what we call transparent objects. Now, what are transparent objects? Transparent objects allow light to pass through. Okay? And we will also look at, is there situations where sometimes certain lights are allowed to, certain color of light is allowed to pass through and some are not allowed to pass through. Okay? We're going to look at that. Apart from transparent objects, we also have opaque objects. Opaque objects do not necessarily just allow light or different colors of light to pass through, but what they do, they absorb certain colors of light. And as they absorb certain colors of light, they also reflect certain colors of light. Now, such types of objects contain what we call pigments. And when we talk of transparent objects, we can talk of filters. Filters allowing light, certain lights or colors of certain colors of light, okay, allowing some colors of light, to pass through. So that's what we have. We have a situation where we've got objects that would say this color is not going to pass. We're going to send it back, but this color can pass through. And because certain colors can pass through them, we say they are transparent. Now we have objects which would say we're not going to allow colors or any other colors to pass through, but what we'll do, we'll absorb certain colors and allow certain colors to be reflected back, right? So those are the types of objects we have when we look at color and color subtraction. Right, let's look at example 4. A beam of cyan light is shown from a light source onto a white screen. The first question is, what are the primary colors of light that produce a beam of cyan? Now, beam of cyan, we can refer on our colors, again, wheels of color. Here, this is where cyan is. Now, which two primary colors are forming that? We can see you've got green and you've got blue. So the answer to that would be that we have got the primary colors forming cyan as green and blue. So when we have those primary colors, we're going to have cyan color. That gives us cyan. Now, the question moves on to say transparent filters of primary colors are placed in the path of the cyan beam. So before the cyan beam reaches the screen, you've got these filters along the way. Predict what color of light will be seen on the screen when the following filters are used. So say you have got that cyan light coming and you have got a blue filter on the way. Now let's look at this. Here is the cyan light coming. You've got a blue filter, right? So you've got a blue filter on the way. Allow me to use this as representing a blue filter, right? So if this is blue, just don't have a nice blue color here with me, but say that represents blue. And this is cyan coming in. Remember that cyan is made of green and blue. And this filter here is blue. Now, the question wants us to find out, when you have this blue filter here, let's predict what color are we going to see on the screen somewhere there. So there's a screen there where that light is shining. So here we have got, if you like, we have got green and blue inside this cyan going in. So it's green, G for green, and blue, B there for blue. So it's going there. These two form our cyan. When it gets in here, this filter here is going to filter the colors. And what it will do, it's going to allow some light to pass through. What light is going to pass through there? It's going to allow blue to pass through. Because there is blue here, this is in blue. What is going to happen to green? Green will be absorbed or will be reflected back here. So green goes back and blue is allowed through. So in other words, your cyan has been now broken up into two of its components. The blue is allowed to pass through and then the green is reflected. In other words, what are we going to see on the screen there? The color that we're going to see on the screen is blue. So we're going to see a blue color on that screen. Okay? Blue goes through. That's what is going to happen. Right now, let's look at the second part of this question. This time, we've got a green and blue filter. It's one filter made up of those two colors. So there is the filter. Okay, again, bear with me. I don't have the colors to show that, but see this as being a filter made up of green and blue. And you have your cyan beam of light, ray of light coming in that direction, right? It hits the filter. The filter is made up of green and blue color. Now there's a screen there that's going to help us see what color of light is being formed when this cyan beam of light passes through that filter. Now remember that cyan is made up of blue and green. So made up of blue and green. There we go. Here is cyan made up of blue and green. Now this filter we're talking about is also made up of green and blue. So green and blue is going to pass through here. So if green and blue pass through here, they are definitely going to add together. And what are we going to see forming on the screen? It's actually the cyan color. So we'll still see the cyan color. So if we want to see that color after going through the filter, we need to make sure that that filter is always made up of green and blue colors. Right. Let's come to number C of our example, example 4. What filter would you use if you wanted to block out the cyan beam? Right, you've got a cyan beam. You don't want any of it to pass through such a filter. What kind of a filter are you going to use there? Now, if you go back to the colors, you will see that cyan is there and it is opposite red. That's how it is positioned. It is made up of green and blue, and it has got nothing, completely nothing to do with red. Now, if we are to block the cyan completely, what filter can we use? I think that is already giving you a clue. The filter we're going to use to block out the cyan beam completely so that we don't see anything on the screen, we see black. What is going to happen is we're going to use a filter made up of red color, because the red color is not going to allow green to pass through. It's neither going to allow blue to pass through. So that's what we're going to do. We're going to use a red filter to block out the cyan completely. Right. Now let's proceed. We're going to have a look now at more on color, of course, but then we're going to look mainly at the subtraction of the color of light. Let's have a look here. Talking about subtraction, removing, okay, color. And this subtraction can be, or is related to absorption of color, all right? So color is being absorbed. Here, when color is being absorbed and color is being reflected, it helps us to see the color of objects. For us to see colors of objects, it's because objects are actually absorbing certain colors and are reflecting others. And what we see are the reflected colors. Let's have a look at this diagram here. Now, this diagram here, the first part, we have got red here. So in other words, we've got some object that is of red color. And that object, for it to have the red color, it has a red color because we are seeing something of red being reflected. Now, let's have a look at it. Remember that the primary colors of white light, which is what we see, what helps us to see that white color, is the red, the blue, and the green, RBG there. When the white light is shone on this object here, because this object has got the ability to reflect the red, what happens is that it's going to absorb green and it's going to absorb blue. So those two are absorbed. And what is going to happen? The red, this one, is reflected. Now, when it is reflected, remember this red is a ray of light. It is reflected, and then it comes onto our eyes, and we see that reflected color. And we see this object as being red. These two, the blue and the green that are absorbed, we can actually say, in terms of how we've written it down here, and it's of course scientifically accepted, we can say that those colors have been subtracted. And what things are actually doing this subtraction and or absorption and also reflection of colors? These are substances called pigments that are found in our clothes, in so many objects that actually give those particular objects color. Let's look at this black one. What happens for us to see something as black? In other words, absence of color. What happens is that you have your white light made up of your primary colors again, your red, your blue, and then your green. But then these black object, or this object that appears black, what it does, it absorbs. So all of these, red, blue, green, absorbed. Remember the word I used earlier on again? Subtracted. So that object subtracts all those primary colors. And when an object subtracts these primary colors, which form the white color, it means there is an absence of light. Absence of light. And if you have absence of light, whatever you see is black. Hence, this black object here. Right, let's come to the white one. Here is the white object. It appears white because, remember, the primary colors of white light, red, blue, green. They come in, all of them are reflected. So all reflected. None of them is absorbed or subtracted. So because all the three are reflected, and the three we know they come together to give us white, it makes us to see this object as white. It could be a white shirt, a white mug, white whatever. Okay, so that's how we see or perceive objects around us. Let's quickly talk about pigments because this is so related, and then we're going to have some example later on. Pigments. Now, pigments, let's have a look at that. Remember that we have the primary colors. This is your green, this is your red, and this is your blue. Now, these primary colors are primary colors of light, okay? But then, and then when we mix the light together, remember when we had blue and red, we had magenta, and we had green and blue, we had cyan, and we had red and green, we had yellow. But then with pigments, that changes. What we know as being primary colors for light are not primary colors for pigments. Okay? We call them subtractive primary colors for pigments. And these primary colors are actually what we knew as secondary colors for white light. So these are primary colors for our pigments. We've got magenta, yellow, and then we've got cyan. Right? Now, this primary color or this primary pigment color, it will always subtract green from light. This primary color of the pigment called yellow will always subtract blue. It will take out blue from light. Cyan, in the same way, is going to take out red from light. Okay? Now, let's look at the subtractive secondary colors. Now, red, blue, green, primary colors of light. For us to get to red, we need to mix magenta and yellow. Okay? We will get red. For us to get blue, we will mix magenta and cyan. For us to get green, we can mix, or we will mix yellow and cyan. Okay, now let's look at this picture here. Let's go back to it. Here it's, in other words, what we're saying is that this yellow, this cyan, and magenta there, this becomes primary subtractive colors, or primary colors when we talk pigments. For pigments, these are primary colors. This is where we start. So if we want to have red color, when we have our pigments here, and this is how paint works. Paint works from here. If we want to have a red color, we're going to add yellow to magenta, so we get red. If we want a blue color, we're going to add magenta and cyan. If we want a green color, we're going to add cyan and yellow. Then we have that. That's how it works there for pigments. So that's very important for you to understand, because the primary colors for pigments are actually not the same as the primary colors of light. Okay, so primary colors for pigments, magenta, cyan, yellow. Primary colors for light, it's red, blue, and green. Okay, now let's move on and have an example. Example 5, a shirt appears magenta with 2 green stripes in white light. Now, so it's white light shining on a shirt. So the white light, remember, we've got red, we've got green, we've got blue. So all these is shining on the shirt. But then magenta, we know, is going to, for it to appear magenta, it means 2 colors are reflected back. And what 2 colors gives us magenta? The 2 colors that gives us magenta is red and blue. So it means that the shirt here, shirt is reflecting red and blue, okay? But then this green would have been absorbed, but then there are stripes, there are green stripes here. So where those stripes are there, even green comes back on those stripes. So all this is on the shirt. That's what we're trying to establish here. It's on the shirt. Now, if instead of this white light, we have got blue light, so just blue, only blue coming here. Now, magenta is made of red and blue. That's magenta. So that's the main part of the shirt. It's not the stripes. We're going to see the main part of the shirt being blue, because blue is going to be reflected here. So we're going to see that blue color of the shirt. Then the question is, what is going to happen to the stripes, the 2 green stripes? Now, well, blue doesn't have anything to do with green, and therefore these green stripes here are going to be seen as absence of color. And what is absence of color? Black. So we're going to see blue, the color, the shirt, the main color of the shirt being blue, and these stripes being black. So that's what is going to happen here when we have a blue light. We're going to have the shirt, the main color being blue, plus black stripes. That's what we're going to see. Right. Now, if we have a yellow light, what is going to happen? Now, we need to be quickly careful about yellow, because yellow would have, what are the colors for yellow? We have red and green. Okay? So here is the shirt. Okay? It is magenta when it is white light. So it has got, again, blue and red. Okay? In white light it's magenta, and it also had the green. Now, this yellow here will go in. You would see that red is there, so it will be reflected. So we'll see some red in the main color. Let's come to the stripes. Those 2 lines there represent the stripes. We have got green. So it's going to be red with what? There is green here. Green will be reflected off the stripes. So we'll see the stripes as being green. So what we will see here, the main color of the shirt this time will be red, plus what? Green stripes. So the green stripes will be, we will see there, red and green. Now, the last question on example 5, B, can you use light Can you use light to make this shade appear black? Explain your answer. Can we do that? Can we make it look black? It's not possible. We cannot make it look black, right? Why can't we make it look black? The shade in white light has got magenta, which is blue and red and green stripes. That's what it has. So if we bring all the colors here, the white light, that's what we'll see. If we bring any other color, say we bring a green one here, right? We will see the two stripes, but that will be black. There will be nothing to reflect for those. So if we can't see the green stripes, we're going to see the blue and red color in some way. So there is no way in which we can see the shade here as completely black. In other words, we cannot have complete subtraction of color there. It is not possible. So thank you so much. And I mean, on that note, we're bringing our lesson to the end. I hope you enjoyed it. Color is very interesting, but can be confusing at times when you don't give yourself time to go through it, exercise, practice. I think that is what you need to do on your own. There will be examples, of course, on your X sheet. Please go through that. Work it out on your own. Also work out on the exercises that are there. They are going to help you.